In this video, we discuss the quantization distortion. Let's look at the example that 8-level quantizer that we designed. In this example, if the signal values in between 0 to 2, we assign the quantization level of 1. So in this case, there is an error involved because the signal values can be anything between 0 to 2, but we all round it up to 1. So therefore, the error, we call it error x tilde, that equals to x minus x hat. X is the value of the signal, x hat is the level assigned. In this case, x is in between 0 to 2, and x hat equals to 1. Therefore, we have x minus 1 here. Because x is uniformly distributed, then x tilde is also uniformly distributed. Is uniformly distributed from -1 to 1. This is the range of the error for the quantization. If the value of x is 0 and 1 is assigned, so the error is -1. If the value is 2, the assigned level is 1, so therefore the error is 1. But any values in between here, the error is in between -1 to 1. And then let's look at a general case. This is 8-level quantizer as well. If the signal value is in between 0 to theta, the level assigned is this level, that's half theta. When the value of the signal is in between 0 and theta, the level assigned is half theta. In this case, the error x tilde equals to x, that's the value of the signal, minus x hat, mean x in between 0 to theta, x hat equals to theta half. So therefore, x tilde is in between minus half theta to half theta. That's uniformly distributed because the value of x is uniformly distributed from 0 to theta. Now we understand that the error is a random variable, is uniformly distributed in minus half theta to half theta. Now we define a measure for the quantization distortion. We want to take the difference of the signal and the assigned level, we take square because the difference can be positive or can be negative, but we want square them such that it's all positive. This distance between the signal value and the assigned level is equals to x tilde squared. X tilde squared is uniformly distributed. So the PDF of x tilde will be minus half theta, and this is rectangular. What's the magnitude? The magnitude is 1 over theta because we want the area of the PDF function equals to 1. And zeros outside this range. To measure the quantization distortion, we define the signal to quantization noise ratio as SQNR. Here the terminology noise does not refer to the thermal noise, it only refers to the quantization error. So SQNR is the ratio of the expectation of signal squared and the expectation of the error squared. And we know that x tilde is uniformly distributed in minus half theta to half theta. We can calculate the expectation of x tilde squared. We do integral from minus half theta to half theta. And integrand x tilde squared multiplied by the PDF function 1 over theta. The integral equals to theta squared divided by 12. And we can plug this in here. That's equals to expectation of x squared divided by theta squared divided by 12. We know theta, this is a quantization region. For 8-level quantizer, theta equals to 2xm divided by 8 8 is the number of the intervals, the number of level of the quantizer. If for n level of quantizer, theta equals to 2xm divided by n. This big n, that's the number of levels in the quantizer. So we plug it in here. Theta equals 2xm divided by n. Now we plug the value of theta. This is a theta squared, and 12 is here. Reorganize the numbers a little bit. That's 3. Expectation of x squared still here. And then in the denominator, x m squared, and n squared is here. N is the number of the levels in the quantizer. Now let's do a little recap here. Signal to quantization noise ratio. Loosely speaking, that is a ratio of the power in the signal and the power in the quantization error. The smaller of the error, the smaller the denominator. So the bigger the SQNR. The bigger the SQNR, the better performance of the quantizer. Our derivation shows that SQNR is related to the number of quantization levels. If the quantization level increase, the SQNR increase. That is desired. Next, let's introduce the relationship of the number of bits for the quantizer and the number of the quantization levels in a quantizer. The number of bits is small n. The number of levels is big N. We have 2 to the power small n equals to big N. Therefore, we have n squared equals to 4 to the power of small n. Replace n squared by this number, 4 to the power small n. We obtain the relationship SQNR related with the number of bits in the quantizer. If the number of bits in the quantizer increase, the SQNR increases as well. Let's look at more the relationship of the number of bits in the quantizer and the SQNR. To have that, we want to express the SQNR in decimal, in dB. So we take the SQNR, this is a value, real value. We take 10 log 10. So 10 multiplied by log 10 based. This portion equals to 10 log 10. I omitted base 10 here because here I have it on this side. It's pretty much clear. So this portion that's here, 10 log 10. This portion that equals 6 yen. Take logarithm. This portion that equals to 4.8 dB. This is a constant. Using this relationship, we can see if the number of bits in a quantizer increase by 1, the SQNR increase 6 dB. This relationship helps us to determine the number of bits for a quantizer given a target value of SQNR. Next, let's consider an example. We consider an 8-level quantizer. Signal values x is in between -8 to 8 and is uniformly distributed. We want to find SQNR in this case. So the SQNR, this is the formula we just discussed. We need to find expectation of x squared and xm squared. In this case, xm equals to 8 because the range of the signal is from -8 to 8. So exm equals to 8. The signal, it is uniformly distributed. So the PDF function is 1/16 in -8 to 8. So expectation of x squared, we do this integral. And this integral is equals to 1/3, 8 to the power third, and plus 8 to the power third, and 1/16 here, 1/16 still here. We do a little reorganization here, and this quantity equals to 8 squared divided by 3. Now plug it in the SQNR, 3 multiply, because we have 8 levels, so the number of bits is equals to 3. Plug it in, we have SQNR equals to 64. What's in dB value? We take 10 log 10, we have 18 dB. Now, the same signal, if we use 16 level quantizer, in this case, the number of bits is 4. So other quantities are remain the same because we quantize the same signal, the same range, as the same values. So therefore, the SQNR equals to 256 now. The dB values, if we take 10 log 10, that equals 24 dB. We look at the results from equation 1 and equation 2. The quantizer increased 1 bit, the SQNR increased 6 dB. And this is exactly what we derived in the slides.